Good evening, friends. Welcome to day 11 of the Six Sigma Masterclass LH sessions. So today we are going to look at the exercises under testing of hypothesis as well as correlation and regression analysis. So all these exercises that we are going to solve in today's session, these exercises will not appear as questions in the black belt final assessment, but then it's important for you to learn how to tackle these case scenarios as a Six Sigma black belt, right? So it's important that you learn how to solve all these case scenarios, even in the practical work-related scenarios that you would encounter, right, in your day-to-day work. So let us get started. So let me just share my screen. So straight away go to the exercise file. And we are going to click on the next sheet in the exercise file, which is titled One Sample T-Test. Fine. So as I have done for majority of the statistical concepts, I have just given the procedure to perform the calculations using the manual formula as well as using Minitab, right? So this is exercise number 1 under one sample T-test. So the weight in kilograms of the units produced pertaining to a manufacturing process is normally distributed with a sample mean of 12 kgs and a sample standard deviation of 2 kgs. If the sample size is 30, test whether the mean weight of production is greater than 10 kgs. So this is the question asked. So we have been provided with the sample data and we have been asked to validate whether the population mean weight of production is greater than 10 kgs. Now we will know that this is a one sample t-test because this question appears under one sample t-test, right? But then if this had been an independent case scenario, then how to identify that this is a one sample t-test exercise? So that is very, very important. So even in the green belt assessment yesterday, you would have got some couple of questions pertaining to identification of the appropriate hypothesis test for a given case scenario. So it will be the steps that I'm going to tell will be very, very useful for you, even to identify the appropriate hypothesis test logic that we are supposed to apply for solving a case scenario. So step number 1. First and foremost, we need to identify the statistical metric that needs to be validated in this case scenario. So I will just kind of write the question and also simultaneously provide the answer. So identify the statistical metric to be validated, right? So what is the statistical metric to be validated in this case scenario? So if we look at the second part of the question, so it clearly says that we need to test whether the population mean weight of production is greater than 10 kgs. So mean is the statistical metric that we are supposed to validate in this case scenario. Another information that would confirm that we can apply mean as a statistical metric is that we find that the weight data is normally distributed. So the data, that is the weight data, is normally distributed. So this is yet another confirmation that we can apply mean as a statistical metric. So I will provide the answer here. Mean is the statistical metric to be validated, and the weight data is also normally distributed. So this is another piece of information that would help us to reconfirm that we need to use mean as the statistical metric here, and this is what we are supposed to validate. Now step number 2. So we need to identify how many sets of sample data have been provided in the case scenario. So how many sets of sample data have been provided, right? And as we can see, we have one sample mean value, one sample standard deviation value, and one sample size value. So it clearly indicates that There's only one set of sample data that has been provided in the case scenario. So one sample mean, one sample standard deviation, and one sample size. So this would indicate that the samples are drawn from a single population category. And another thing is we have been asked to validate whether the population mean weight of production is greater than 10 kgs. So in case of one sample mean test, we will validate whether the population mean is equal to some target value. And that is what we have been asked to validate in this particular case scenario as well, right? So hence we can identify that this is a one sample mean test. So there is only one set of sample data provided in this case scenario, and we have been asked to validate whether the population mean is greater than a certain value, right? Or it can be very specific, is greater than 10 kgs. Hence, this will be one sample mean test. But then under one sample mean test, as we all know, we have z test and t test. So under one sample mean test, we have z test and t test. So which one to apply? So as I told you, when we discussed about the list of, or when we discussed about the hypothesis test for mean, so I had mentioned this very clearly that if the population standard deviation is known, then we can use z-test. But then if you are provided with only the sample standard deviation, then we need to apply t-test, right? So the population standard deviation is known, we can use z-test. But if you are provided with only the sample standard deviation, then we need to apply t-test for that scenario. So here in this case scenario, it's very clear that we have been provided only with the sample standard deviation and not the population standard deviation. So we need to use t-test for this scenario, and hence this will be one sample t-test. So step 3, identify whether we need to apply Z or t-test. So the answer is, since the sample standard deviation has been provided, we need to apply t-test logic, right? And hence, this will be one sample t-test exercise. So this is how we need to identify the appropriate hypothesis test logic that we are supposed to apply for solving a case scenario. So this will be one sample t-test exercise. Now, having decided that this is a one sample t-test exercise, now we can start the calculation part. So we will first frame the hypothesis statements. So the problem would actually, the answer part would actually start by framing the hypothesis statement, right? So the steps that I mentioned will not be part of your answer. So these steps are more for your understanding as to how you are supposed to identify a particular hypothesis test logic in order to solve a case scenario. So the actual solution part for a hypothesis testing exercise will start by framing the hypothesis statements. So what will be the null and alternate hypothesis statements for this scenario? So we will denote null hypothesis by this notation H naught. So you'll put H naught colon, means that we are going to state the null hypothesis. So here we are validating the statistical metric called mean. So we need to incorporate the population notation for mean in the hypothesis statements. So what is the population notation for mean? So you should not forget. So it is mu. So this is the symbol for mu. So mu equal to 10 kgs, right? So whenever we frame the null hypothesis, we always need to put the equal to sign for it. So it's very easy for us to frame the null hypothesis because we just need to close our eyes and then put equal to sign. So irrespective of whatever is the case scenario, null hypothesis will always take equal to position. That's a characteristic of null hypothesis. So even here, when we frame the null hypothesis, whatever value we are trying to validate, so we just need to put the equal to sign for null, right? So you put the population notation of that statistical metric and put a equal to sign. So that will be my null hypothesis, right? But then whatever we are supposed to prove will be my alternate hypothesis, HA, right? So what is that we are supposed to prove? The second part of the question clearly mentions that. So we have been asked to validate whether the population mean weight of production is greater than 10 kgs, right? So this is what we are supposed to prove in this case scenario, that the population mean weight of production is greater than 10 kgs. So mu equal to 10 kgs will be my null hypothesis. But the alternate hypothesis we need to remember can take one of these three signs. What are the three signs possible for alternate hypothesis? It can either be not equal to, or less than, or greater than, right? Depending on the case scenario. So the alternate hypothesis sign can either be not equal to, or less than, or greater than, depending on the case scenario. So if the metric is nominal, the better. So the appropriate sign for alternate hypothesis will be not equal to. If it is higher, the better, then the appropriate sign will be greater than, because achieving a higher value will always be challenging. So the alternate hypothesis should be a challenging statement, right? So when you have higher the better kind of metric in the case scenario, so we need to put greater than sign for alternate hypothesis, because achieving a higher value will always be challenging for these kind of matrices. But then if it is lower the better kind of metric, then we need to have less than as the sign for alternate hypothesis, because achieving a lesser value for these matrices will be highly challenging. So here we don't have to really worry about all these things. We don't have to really worry about applying any logic, for identifying the sign for alternate hypothesis. So it is given very clearly in the question itself that we need to validate whether the population mean weight of production is greater than 10 kgs. So the alternate hypothesis sign will be greater than. So simply put, the greater than sign for alternate hypothesis. So while the null hypothesis will always take equal to sign, alternate hypothesis can take one of the three signs, that is not equal to, or less than, or greater than, depending on the case scenario, right? So that is why framing alternate hypothesis will be slightly challenging. So here it is given in a straightforward way, so there is no problem in picking up the sign for alternate hypothesis. But then, if the alternate hypothesis sign is not given in a straightforward manner in the case scenario, then we need to apply some logic in order to identify the sign for alternate hypothesis. So what is the logic that we are supposed to apply? So we need to look at the category of the metric. So the metric category is nominal the better. The appropriate sign for alternate hypothesis will be not equal to. If it is higher the better, then it will be greater than. If it is lower the better, alternate hypothesis sign will be less than. But then as far as this exercise is concerned, the alternate hypothesis sign is given in a straightforward manner. We just need to pick it up from the exercise. That's it, right? So that's what I have done. So even if you look at the metric, the weight in kilograms, it can be considered as higher the better kind of metric. So as we kind of produce, right, larger number of items, right, with some good weight, right, then in that case, it's going to be beneficial for the organization, right? So if you're going to produce, some good number of items with some good weight, it's always going to be beneficial for the organization. So ideally, we can have greater than as the sign for alternate hypothesis. That would be very pretty much challenging for us to achieve, right? So let me just summarize all these sample values. So X bar is this sample mean, which is given as 12 kgs, and then small s is the sample standard deviation given as 2 kgs, and small n is the sample size, which is given as 30. So these are the sample values that are provided in this case scenario. Now, what we are going to do, we are not going to apply any manual formula to perform the calculation, but then if you are academically interested, you can always refer to this particular section, right, wherein I have mentioned the procedure for performing the manual calculation. So you will find the manual formula in this particular section, which can be used for calculations, right? But then we are going to use Minitab and of course our template. So I have provided Excel templates for all the hypothesis tests that we are going to solve today. So even if you do not have Minitab, it's absolutely fine. You can definitely manage with all these Excel templates. So even though these questions are not likely to come in the final assessment, but then, as a Six Sigma black belt, you would be performing all these statistical analysis as part of your project exercise. So in the future, if you want to really, analyze all these kind of case scenarios, then without Minitab, it would be very difficult, right? So it should not be a showstopper just because you don't have the Minitab software. So you should be able to perform the analysis quite comfortably. So that's why I've given templates for all these hypothesis testing exercises. Now let me just show you how to solve this using Minitab. So we open Minitab and then we go to Stat and then Basic Statistics. Under that we have one sample T. So stat basic statistics and one sample T. So we have the summarized data with us. So choose the option summarized data. So sample size is 30. Sample mean is 12 kgs. Sample standard deviation is 2 kgs. And the hypothesized mean, the population mean is 10 kgs. And then we click on options. Just check whether the confidence level is 95%. So I told you very clearly, if nothing specific is mentioned about the confidence level, then we need to consider the default confidence level to be 95%. So here again, in this Minitab dialog box, the confidence level will be given as 95% by default, unless and until you would want to change this, right? But just check whether 95% is the confidence level provided in this Minitab dialog box. And then the alternate hypothesis sign. As I told you, there are three options that we can choose as a sign for alternate hypothesis. So the alternate hypothesis can either be not equal to or less than or greater than. By default, the alternate hypothesis sign will be not equal. But then if you click on this drop down, you can choose the appropriate sign for alternate hypothesis. So this, option is not given for null because as I told you, null will always take equal to sign. There is no problem at all. It's only the alternate hypothesis which can take either not equal to or less than or greater than, and hence this drop down has been provided for alternate hypothesis only. So for this case scenario, the sign for alternate hypothesis is greater than. So choose that sign and click OK at both the places to get the answer. So you will obviously get p-value, right? So Minitab means, you'll be looking at p-value as the output value. So based on this p-value, we need to come up with the final inference. So if you look at the statistical inference, so looking at the p-value, so we will decide either to accept or reject the null hypothesis, right? So I've already, mentioned about the criteria that we need to apply for p-value to take a final call. So p-value is greater than 0.05 for 95% confidence level, we will accept the null hypothesis. On the other hand, if the p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and hence accept the alternate hypothesis. But then here the p-value is 0, right? Which is obviously less than 0.05. So as per the Minitab output, the p-value is 0.000. Now, what will be the statistical inference for this scenario? The statistical inference will be, since the p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis, right? So we need to reject the null and accept the alternate hypothesis for this particular case scenario. But then if you are going to provide this inference to your leadership, they will not be able to understand anything, right? So what is this null? What is this alternate, etc.? So for their benefit, we also need to provide what is called the business inference, right? So we also need to come up with the business inference. So based on the statistical inference, we will frame the business inference. So since we have been asked to accept the alternate hypothesis, so what is the alternate hypothesis statement? The population mean weight of production is greater than 10 kgs. So that is what I'm going to frame as the business inference. So the population mean weight of production is indeed greater than 10 kilograms. So this has been proved, right? So this will be my business inference. So this is how we will solve all these hypothesis testing exercises, right? So analyzing the sample data and making an inference about the entire population. So when we analyze the sample data in Minitab, so we'll be looking at this metric called p-value and then apply the p-value criteria. P-value greater than 0.05 for 95% confidence level, we will accept the null hypothesis. On the other hand, if p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and hence accept the alternate hypothesis. But then if you are going to use this template, so you need to provide all the input values. So before that, please do not even look at the inference here. So the inference, the default inference will always be accept H naught. So we need to provide all the input values in this input section and then look at the final inference, right? So as I told you, so Minitab will stop with providing the p-value. And based on that p-value, we need to take the final decision as to whether we are supposed to accept or reject the null hypothesis. But then if you are using my template, you will also get to see the inference, the final inference, right? And it would vary depending on the confidence level. As I told you, if you are going to reject the null hypothesis at 95% confidence level, there is every possibility that you may accept the null hypothesis at 99% confidence level, right? So as we saw on the other day, that 99% confidence level, so the confidence interval width will become much more wider, correct? So this is what we saw on the other day when we discussed about the confidence level and confidence interval. So as we can see, at 99% confidence level, the width of the confidence interval will become much more wider. So at 99% confidence level, the probability of accepting the null hypothesis will also be very high. It will be 99%, right? So as I told you, so if the final analysis, if the party is going to get 125 seats, right? Say for example, the political party is going to get 125 seats. So the null hypothesis would have got rejected at 95% confidence level. So null hypothesis will get accepted only if the number of seats won by that political party is anywhere between 130 and 170 for this particular example, right? In this example. So if it is going to be 125, then you would have ended up rejecting the null hypothesis at 95% confidence level. But then at 99% confidence level, 125 will still fall in between the interval estimates, right? Because the interval estimate would have become much more wider. So what you may reject at 95% confidence level, you may end up accepting at 99% confidence level, right? So in my template, so that adjustment will be automatically done, right? You don't have to really worry. So if you provide the appropriate confidence level, then it will come up with the appropriate inference for that confidence level, right? So for this, for all the hypothesis testing exercises that we are going to solve today, the confidence level is not mentioned in the case scenarios. So we will consider the default confidence level to be 95%. So what is the sample mean given in the question? 12 kgs. Sample standard deviation is 2. Sample size is 30. Now confidence level is 95%. As I told you, whenever you use Minitab or my template, we need to provide the percentage values in decimal. So this will be 0.95. And the hypothesized mean, which we are supposed to validate, is 10 kgs. Now we need to pick the appropriate sign for the alternate hypothesis from this drop down. So for this scenario, the appropriate sign is greater than. So pick that sign. You will get to see all these values displayed here. So whatever output values your Minitab will give, the same set of output values we can see in this template. So all these are formula driven. So we should not be tampering with this particular section. So all these are formula driven, right? So based on this test stat value, so we will arrive at the p value. Based on this p value, we will come up with the final inference. Now p value is 0, final inference is reject the null hypothesis. That is exactly what we have done by considering the Minitab output, right? So if you look at the test stat value, it is 5.48 shown by Minitab, right? And this lower confidence interval for this will be 11.38, and that is exactly what we are getting, 11.38, right? So all these output values are matching with the Minitab output. So this is how you need to solve the exercise. So if you're using my template, you will be getting the final inference as well. So there is no need for you to remember the criteria that we need to apply for p-value. So you will get the final inference as to whether you are supposed to accept or reject the null hypothesis. So this is one sample t-test. So this is the kind of logic that we are going to apply for all the other hypothesis tests as well, right? So first we will see how to identify the appropriate hypothesis test for a given case scenario. And then we will use Minitab to perform the statistical data analysis, and then based on the p-value we'll come up with the final inference. So we will frame both the statistical and the business inferences, and then we will see how to use our template by providing the input values and looking at the inference in the solution section. Now let us proceed to the next one. So click on the next sheet. So we have two sample t-test and f-test hypothesis exercises. So provided here. So since, we would require similar, kind of matrices as input values for both two sample t-test and f-test. So I have actually combined these two tests as one single test, right? So I've given these two tests as one single test, but then we are going to solve these two tests separately, but it will be under one single exercise. So let us look at this exercise. It says that a bike manufacturing company would like to compare the mean mileage of two brands of motorbikes manufactured by them, brand A and brand B. Assuming that the mileage data is normally distributed, validate the following. So there are two sections to this problem. The first section is asking us to validate whether the variances in mileage of brand A and brand B are equal or not. So whether the variances in the mileage of brand A and brand B are equal or not. And the second section is asking us to validate whether the mean mileage of brand A and brand B are equal or not. So one statistical metric that we are supposed to validate as far as section A is concerned is variance. And the other statistical metric that we are supposed to validate is mean. So that is part of section B. So first we will look at section A. So here we have been provided with the sample data pertaining to both brand A and brand B. So if you look at this table, so we have the sample mean, sample standard deviation, and sample size provided for both brand A and brand B. So two sets of sample data have been provided to us in this case scenario. So now let us look at section A. So when we have, two sets of sample data, so it will be two sample tests, and we need to validate the metric called variance. So it will be two sample variance test. So as far as section A is concerned, the statistical metric that we are supposed to validate is variance, and we would be comparing the population variances of two sets of or two population categories, brand A and brand B motorcycles. So section A will be two sample variance test, and which is what we would call as the F test. So two sample variance test is also referred as F test. So how did I arrive at this particular two sample variance test? So step number one. So I'm not going to repeat the questions here. So you can refer to the one sample t-test and then see the question. But I'm going to just provide the inference alone for each and every step. So the first step will be to identify the statistical metric that needs to be validated in the case scenario. So here, variance, the statistical metric to be validated as far as section A is concerned. Now, step two. How many sets of sample data have been provided in the case scenario? Two sets of sample data. So two sets of sample data have been provided in the case scenario. And what are the two sets of sample data? That is brand A and brand B. So it's given in this table here, right? All these input values have been given in this table. So hence, this is two sample variance test or F test, right? So having decided that this is a two sample variance test exercise, now we need to frame the hypothesis statements. So what will be H naught? So what is the notation that we are supposed to use for variance? So we need to use the population notation for variance, which is sigma square, right? So we are going to compare the variances of brand A and brand B. So we need to apply the symbol sigma square, right, for population variance. So sigma square of brand A is equal to, so null hypothesis, we will always put the equal to sign. So sigma square of brand A is equal to sigma square of brand B. When it is not yet proved, I will only assume that both the variances are equal. So sigma square of brand B. Now, what will be the alternate hypothesis? So if you look at the question here, so it is given in a straightforward manner. So when it is given in a straightforward manner, then there is no need for us to apply that logic, right? So what is the straightforward manner? Variances in mileage of brand A and brand B are equal or not. So we need to validate whether the variances are equal or not equal. That's it, right? So the appropriate sign for alternate hypothesis will be not equal to. So just copy paste the same statement and then change the sign alone. So the alternate hypothesis sign for this scenario will be not equal to. Why it is not equal to? Because you have been asked to validate whether the variances of brand A and brand B are equal or not. That's it. So we have not been asked to validate whether the variance in mileage for brand A is greater than that of brand B or less than that of brand B. We have been asked to validate whether the variances of these two brands are equal or not. That's it. So the appropriate sign for alternate hypothesis will be not equal to. Now let us provide all these sample input values in the Minitab dialog box. And for this F test or two sample variance test, we would require only the sample standard deviation and the sample size for both the categories. But then when we provide the input value, the Minitab dialog box, we need to provide the sample variance and not the sample standard deviation. So we can calculate the sample variance from the standard deviation value. So variance will be square of the standard deviation value. So 2.05 square, right? So 2.05 is the sample standard deviation for brand A. So 2.05 square will be the sample variance for brand A. Similarly for brand B, so we have 2.15 as the sample standard deviation for brand B, and 2.15 square will be the sample variance for brand B. So 2.15 square. So square root of variance is standard deviation. Standard deviation square will be your variance. Now, having obtained the variance values, now I can use the Minitab and provide all these input values in the dialog box. So again, we need to go to Stat, Basic Statistics, and then we have two variances. Click on that. So again, we have the summarized data with us. So provide the input values. So sample size, as we can see, for brand A, it is 55, and for brand B, it is 60. Just incorporate those values here. So the first category is brand A, second category is brand B, 55 and 60. And since I told you it will ask for the sample variance value to be provided as input value, so we are converting standard deviation in terms of variance. So what is the sample variance? For brand A, it is 4.2025. For brand B, it is 4.62. So 4.2025 and 4.62, right? And we need to go to options, check whether the confidence level is 95%, and we can straight away click OK at both the places and look at the p-value. So what is the p-value? It is 0.726. It is displayed in the form of a graph. So the p-value is 0.726. So as per the Minitab output, the p-value is 0.726. So what will be a statistical inference based on this p-value? So we will say since the p-value is greater than 0.05 for 95% confidence level, we will, what will be a decision? We will,
Consider null.
yeah, accept the null.
The
Yeah,
null.
accept the null hypothesis, right? And what will be a business inference? The business inference will be the population variances in the mileage of both brand A and brand B bikes are equal because we are accepting the null hypothesis. So it has been proved that the variances are equal, right? So this is how we will perform the two sample variance test. But then if you're using the template, it is given right below this exercise. So we just need to provide the input values alone, and then we will get the answers populating in the solution section. So here in our template, we need to provide the standard deviation value. So what is the standard deviation for brand A? 2.05. For brand B, it is 2.15. So you can see this input table. So standard deviation for brand A is 2.05. For brand B, it is 2.15. So that is what I've incorporated. Sample sizes 55 and 60. That's it. These are the values that are required for this two sample variance test. Now confidence level is 95%. We can retain it as it is. But then we need to choose the appropriate sign for alternate hypothesis. So for this scenario, the sign for alternate hypothesis is not equal to. Just moment you provide that sign for alternate hypothesis, you can look at this solution section and also the inference. So the p-value is 0.725 and the inference is accept the null hypothesis. So that's what we also got, right? That can be slight rounding of error, as I told you. So that whenever you have a value with all these decimal places, so there could be slight rounding of error till the the first decimal or second decimal or third decimal. So we have a rounding of error here as well, the third decimal place. So 0.725 or 0.726, both are pretty much similar, right? So we will be accepting the null hypothesis. So that is what your final inference says in this template. Now moving on to section B. So this is section A, right? So section B, we have been asked to compare the mean mileage, the population mean mileage of two different categories, brand A and brand B. So we need to apply two sample t-test. So for section B, it will be two sample t-test. So how did we arrive at two sample t-test? So step number one. What is the statistical metric that we are supposed to validate as far as section B is concerned? Mean is the statistical metric to be validated, right? And step number two. So how many sets of sample data have been provided in the case scenario? Two sets of sample data have been provided in the case scenario. And for the mean test, we will have step 3 as well. So what is step 3? Whether we need to apply z-test or t-test. So since sample standard deviation alone has been provided, we will apply two sample test, right? So this is how we need to identify the appropriate hypothesis test logic that we are supposed to apply for a case scenario. Now that we have identified that this is a two sample t-test exercise. Now how to frame the hypothesis statements? So in the same way as the two sample variance test, right? So what will be the null hypothesis? So what is the notation that we need to incorporate here? Anyone? What is the population notation for mean?
X
What
bar.
is now X bar is sample notation for mean.
Mu.
So it is mu.
It's mu. Yeah.
Yeah, mu. So mu is the population notation for mean. So mu of brand A will be equal to mu of brand B will be my null hypothesis. So mu of brand A is equal to mu of brand B. So what will be my alternate hypothesis? Again, if you look at the problem, so it is asking us to validate
Not.
whether the
Yeah.
population mean mileage of brand A and brand B are equal or not. So it is not asking us to validate whether one is greater than the other or less than the other. It says that we need to validate whether they are equal or not. So not equal to will be the appropriate sign for alternate hypothesis. So let me just copy paste the same statement here and change the sign alone for the alternate hypothesis, which will be not equal to. Right? So having framed the null and alternate hypothesis statements for this two sample t-test, we can provide the input values in the Minitab dialog box. So for two sample t-test, we would also require the sample mean for both brand A and brand B. So the sample mean value for brand A, it is 48.5, and for brand B, it is 49.8. So even these values we need to incorporate in the Minitab dialog box. So we go to stat, basic statistics, and we find two sample T. Just click on that. So we have the summarized data with us. So choose summarize data. So sample size for brand A is 55 and for brand B it is 60. Sample mean for brand A it is 48.5 and for brand B it is 49.8. And the sample standard deviation for brand A it is 2.05 and for brand B it is 2.15. And we can check on this box, assume equal variances, because we have already proved that the variances are equal when we perform this two sample variance test for the same scenario, right? So we can safely check on this box, assume equal variances, and then we click on options just to check whether the confidence level is 95%. And we don't have to really change the test difference, but we need to ensure that the alternate hypothesis sign is not equal, right? That's it. And we click OK at both the places. And we get to see the p-value here, which is 0.001. So this p-value is displayed here, 0.001. So p-value is less than 0.05 for this two sample t-test. So as per the Minitab output, the p-value is 0.001. So what will be a statistical inference? The statistical inference will be, since the p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis. So your statistical inference will be, since the p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis. And what will be your business inference? So the business inference will be the population mean mileage of both brand A and brand B are not equal, because we are accepting the alternate hypothesis, which says the mean mileage of both these brands are not equal. So the population mean mileage of both brand A and brand B are not equal. So that will be my business inference. Right? But then if you're using the template, so the template is given right below this exercise. So two sample t-test template. So what is the sample mean given in the problem? So for brand A it is 48.5, brand B it is 49.8. Sample standard deviation is 2.05 and 2.15. Sample size is 55 and 60. So all these input values are given here in this table for both brand A and brand B. So that is what I have incorporated here. And the confidence level is 95%. What is the sign for alternate hypothesis? It is not equal. So moment you provide the sign for alternate hypothesis, we can look at the solution section. So p-value is 0.001. That is exactly what we also got from the Minitab output. And the inference is reject the null hypothesis. And that is exactly what we did, right? So you'll also get to see the inference at the end. So you don't have to really remember the criteria that you're supposed to apply for p-value and take a decision as to whether you need to accept or reject the null hypothesis. So this template will provide the final inference as well. And this final inference, as I told you, will adjust itself based on the confidence level, right? So as I told you, something that is getting rejected at 95% confidence level can get accepted at 99% confidence level, right? So it's quite possible. So the inference will accordingly adjust based on the confidence level that you would actually incorporate here in this input section. So minus 3.31 is the test stat value. And that is what Minitab has also given, minus 3.31. And we use this metric called pool standard deviation, which is 2.1028. And if you look at our template, rounding it off, it will be 2.103. Fine. So let us move on to the next one, which is paired t-test. So what is the difference between two sample t-test and paired t-test? So in two sample t-test, we would be comparing the population means of two different population categories. But then in a paired t-test, we would be comparing the population means of two different scenarios existing in a process, right? So that is the key difference between the two sample t-test and the paired t-test. So let us look at this exercise under paired t-test. So it says a process has been automated in parts and the team wants to validate if there is any significant benefit due to automation. So a sample of 30 associates were picked for this exercise and the processing time recorded by them were compiled during the pre and post automation scenarios. Validate whether the part automation has yielded any benefit. Right? So whether the automation is successful or not. Now, when we consider processing time as the metric, so what should be the processing time in the post-automation scenario compared to the pre-automation scenario? The processing time should have increased or should have got reduced for the automation to be successful. So if the
Reduced.
automation was successful,
Reduced.
the processing time post-automation should have got reduced or should have got increased.
Reduced.
Reduced, right? It's a simple thing. So the processing time in the post-automation scenario should have reduced significantly compared to the pre-automation scenario. So then only we can say that the automation is successful. And this is exactly what we are going to frame as the alternate hypothesis, because we need to prove that the automation is successful. So when can we say that the automation is successful? Only when the post-automation processing time is significantly lesser than the pre-automation processing time. But then if you are going to place pre-automation as the first category, so this can be rewritten as pre-automation processing time is greater than the post-automation processing time, right? So if this statement is proved, then we are going to infer that the automation is successful, right? So here again, we will write down the steps as to how did we identify that this is a paired t-test exercise. So step number one, mean is the statistical metric to be validated. So you're talking about mean processing time. And then step number two. So we need to, so two sets of sample data have been provided pertaining to two scenarios existing in a process. Hence, this will be paired t-test. Right? Hence, this will be paired t-test. So how will you frame the null and alternate hypothesis for this paired t-test scenario? So the null hypothesis H naught will be H naught colon. So what is the metric that, or what is the population notation that we need to incorporate here? So mean is the statistical metric. So we'll be using the population notation called mu. So mu of pre-automation is equal to mu of post-automation. So without, proving that the processing time during the post-automation scenario has reduced significantly compared to the pre-automation scenario, I will only assume that the mean processing time for both the scenarios are equal, right? So this will be mu of pre equal to mu of post, right? Will be my null. So what is that we are supposed to prove as part of alternate hypothesis? You are going to tell me. So tell me how to frame the alternate hypothesis. When can you say that the automation is successful?
The post is greater.
Post mean processing time is
Should be greater, yes.
Greater.
greater or lesser? Post automation mean
Sorry,
processing time should be,
Yes.
you're talking about processing time.
Yeah,
okay. I guess what he means is, or I mean is, there should be a greater than sign in between the mu pre and
And
mu
mu
post.
post.
Yes.
Fine. No, that is correct. I'm not saying that it's incorrect. But then what is that? We are actually trying to prove here that mu post is less than mu pre. So since
Exactly.
we are
Exactly.
having mu pre as the first category, so we need to retain it for alternate hypothesis as well. Because mu pre will be my first category. So instead of writing this as mu post is less than mu pre, I can also rewrite this as mu pre is greater than mu post.
Yes, yes.
Now you are understanding, right, why it is so challenging to frame the alternate hypothesis. All the other earlier problems, it was given in a straightforward manner, so there was no issue at all. Now here is the tricky thing, right? So if you want to prove that the automation is successful, then what should be the appropriate sign that we need to provide for alternate hypothesis? And if you're going to place mu pre as the first category, then what should be the sign? So this will be mu pre greater than mu post. Right? So mu pre greater than mu post. So it can be either mu post less than mu pre or mu pre greater than mu post. Since we are placing mu pre as the first category while framing these hypothesis statements, so I need to have mu pre as the first category while framing the alternate hypothesis statement as well. So this will be mu pre greater than mu post, right? So this will be my null and alternate hypothesis statements. Now I can perform the analysis using Minitab. So for that, so let me just copy paste the processing time values for 30 associates pertaining to the pre-automation and the post-automation scenarios. So let me just copy paste in the Minitab worksheet. And then we need to go to stat, basic statistics, and we find PAT-E. Click on that. So the samples, it is not a summarized data because we have been provided with all these raw data points pertaining to the processing time for both the scenarios. So we can say that these samples in columns. So the first sample is pre-automation processing time data, and the second sample is post-automation processing time data. And we click on options. Confidence level is 95%, and the test mean can be 0. And the alternate hypothesis sign, here it will be greater than. Mu pre is greater than mu post is what we are trying to prove. So the alternate hypothesis sign will be greater than, right? And then we need to click OK at both the places to look at the p-value. So p-value is showing as 0.000. So let me frame the final inference. So as per the Minitab output, the p-value is 0.000. So what will be a statistical inference? The statistical inference will be, since the p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis, right? And what will be a business inference? The business inference will be the population mean processing time in the post-automation scenario has significantly reduced compared to the pre-automation scenario, right? And hence, the automation exercise is successful. Hence, the automation exercise is successful. But then if you are solving this using our template, so we need to provide the input values as given in the case scenario. Just copy paste the input values alone for all the 30 sample associates in this table. It's given here. So moment we do that, the answers will get populated automatically. So the alternate hypothesis sign is greater than, and then we find the p-value here. So t-testat value is 9.60. So that is what Minitab is also displaying here. T-testat value is 9.60. So based on this, we will calculate the p-value, which is 0.000, and the final inference will reject null hypothesis. So Minitab doesn't give the final inference. We need to frame applying that criteria. But then if you're using my template, even the final inference will be displayed.
What is the significance of t-test stat value?
That is what we would calculate applying the manual formula. So based on this t-testat value, so t-testat value is going to be a larger number or a higher number. Then in that case, your p-value is likely to be less than 0.05. If t-testat value is going to be a lesser value, then it's every chance that the p-value could be a higher value. And in that case, we'll be accepting the null hypothesis. So when we actually perform the calculations using the manual formula, we will also draw the distribution diagram, and we will identify two areas in that distribution diagram. One will be the acceptance area for null hypothesis, and the other one will be the rejection area for null hypothesis. And then we will calculate this t-testat value and see where this t-testat value would fall in the distribution diagram, whether it would fall in the acceptance region or rejection region of null hypothesis. So if it falls in the acceptance region, we will accept the null hypothesis. If it falls in the rejection region, we will reject the null hypothesis. So when we perform the calculation using the manual formula, there is no need for us to calculate this p-value. So we will be able to look at the diagram and see where the testat value would actually fall, and accordingly frame the decision as to whether we need to accept or reject the null hypothesis. But then if you are going ahead and calculating the p-value by applying Excel formula, we can do that and we can reconfirm on that decision, right? So because p-value will be calculated based on this testat value. So as I told you, the testat value is very, very low, is a lesser value, then the p-value could be a higher value. So it should be, or it could be greater than 0.05 for 95% confidence level, wherein you will accept the null hypothesis. But then if the testat value is a very high value, then the p-value could be less. And that is what we get to see here. So that is the relationship between testat value and p-value. At what point, the p-value is going to cross 0.05. So at what point that we have for testat value, we will have a scenario where the p-value is going to exceed that 0.05, something that we can estimate and find out, right? But that will be a borderline case, just crossing that 0.05. So if you get a p-value 0.052, you will not know whether to accept or reject the null hypothesis because this is a borderline case, right? But then p-value 0 is very, very conclusive. So we can safely reject the null hypothesis and accept the alternate hypothesis. So we'll proceed to the next one, which is one proportion test. So as we all know, that proportion is a metric that we will use for representing binary discrete data. So we are stepping into the binary discrete scenarios. So exercise number 1, it says a sample study showed that 244 out of 250 units produced adhered to the customer specifications. So test whether the percentage accuracy is greater than 95%. So we have been provided with the sample data, which says that 244 out of 250 units produced adhere to the customer specification. So when we say the unit adhered to the customer specification, it means the unit is an accurate unit, right? So we have the sample accuracy data provided here. And with this information, we have been asked to validate whether the population percentage accuracy is greater than 95%, right? So let us write down the steps. So step number 1, proportion. Because when you say percentage, it means proportion. So percentage accuracy is nothing but proportion of a binary discrete event. So when we inspect a sample unit, the sample unit, as I told you, could be a defective unit or a non-defective unit. Non-defective is what you will call as accurate unit. So proportion of a binary discrete event. Accurate units, right, needs to be validated. So how many sets of sample data have been provided in the case scenario? One set of sample data, because we have the number of events and number of trials. That's it. 244 out of 250 is what has been given. So one set of sample data has been provided. And hence, this is one proportion test. Fine. Now, how will you frame the hypothesis statements for one proportion test? H naught colon. So what is the population notation for proportion? So it will be capital P. So capital P equal to, what is the target value that we are supposed to validate here? 95%. So 95% needs to be written in terms of decimals as 0.95, because we are talking about proportion. Percentage means 95%. Proportion means 0.95. And then HA colon, what is that we are supposed to prove? Accuracy is higher the better kind of metric. So obviously achieving a higher value will always be challenging. So the appropriate alternate hypothesis sign should be greater than, but it is given in a straightforward manner, the question itself. So there is no problem at all. So P, proportion of accuracy greater than 95% is what we are supposed to prove as part of this case scenario. Now we can perform the analysis by incorporating all these sample values in the Minitab dialog box. So open Minitab, go to Stat, Basic Statistics, and then we have one proportion. Click on one proportion. Summarized data is available with us. So number of trials is nothing but the sample size, which is 250. Number of events is the number of units adhering to the customer specification or accurate units, which is 244. And then go to options. Confidence level is 95%, and the test proportion is 95%. So that has to be written in terms of decimals as 0.95. And the alternate hypothesis sign will be greater than for this scenario. And we will check this box, use test and interval based on normal distribution. That is what we will do. And we click OK at both the places to find the p-value. So it is 0.030. So p-value is 0.030. So as per the Minitab output, the p-value is 0.030, right? So p-value is 0.030. What will be a statistical inference? The statistical inference will be, since the p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis. So what will be a business inference? The business inference will be the percentage accuracy for this process is indeed greater than 95%, as we are accepting the alternate hypothesis. So one proportion test template is given right below this exercise. Just need to provide the input values. So number of occurrences is the event. So 244 out of 250. and then the confidence level is 95%, 0.95. Hypothesized proportion is also 95%, so 0.95. And the alternate hypothesis sign for this scenario will be greater than. And we get to see the p-value, which is 0.030. Inference will be reject the null hypothesis. And if you see, the test stat value is showing 1.89. That is what is displayed by Minitab as well, 1.89. Right? So this is how we'll perform the calculations. So we'll move on to the next one, which is two proportion test. Fine. So this exercise says that the defective proportion of a transaction process is compared between shift 1 and shift 2. So the defective proportion of a transaction process is compared between shift 1 and shift 2, and the following sample data has been obtained. Test whether the defective proportion of shift 1 is less than that of shift 2, right? So we have been provided with the defectives data and the sample size, so that we'll be able to calculate the sample defective proportion for both the shifts, right? So let me write down the steps. Step number 1. So proportion of a binary discrete event. That is occurrence of defectives, because we have been provided with the defective proportion. So occurrence of defectives is the binary discrete event, right? Needs to be validated. And then step number 2, right? So how many sets of sample data have been provided in the case scenario? 2 sets of sample data have been provided in this case scenario. And hence, this will be two proportion test, right? So how will you frame the hypothesis statements? So H naught colon. So proportion of defectives pertaining to shift 1 is equal to proportion of defectives pertaining to shift 2. And what will be the alternate hypothesis which we are supposed to prove? It is again given in a straightforward way. The question itself, we have been asked to validate whether the defective proportion of shift 1 is less than that of shift 2. So proportion of defectives of shift 1 is less than proportion of defectives for shift 2, right? So let us incorporate all these sample values in the Minitab dialog box. So shift 1, as we can see, the number of defectives is 5. The sample size is 110. So 5 out of 110. Shift 2, it will be 13 out of 120. So go to Minitab, click on Stat, Basic Statistics and to Proportion, Summarize Data. So number of trials is nothing but the sample size. So 110 and 120. And the number of events, shift 1 it is 5 defectives, shift 2 it is 13 defectives. And click on options, confidence level is 95%, and the alternate hypothesis sign will be less than. And we will click on this box, used pooled estimate of P for the test. And we click OK at both the places. We find the P value to be 0.038. So as per the Minitab output, the P value is 0.038. So what will be a statistical inference for this? The statistical inference will be, since the P value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis. So what will be a business inference? The business inference will be the population defective proportion of shift 1 is indeed less than that of shift 2. So the population defective proportion of shift 1 is indeed less than that of shift 2. So it has been proved. Now if you are applying our template to solve this, just need to provide the input values here. So the number of occurrences for shift 1, it will be 5 out of 110. 5 defectives out of 110. And for shift 2, it will be 13 out of 120. Right? Confidence level is 95% and the alternate hypothesis sign is less than. That's it. So you get to see the p-value and the final inference. And the test at value is minus 1.77. So if you want to validate that as well, it is shown here, minus 1.77. Right? So this is about two proportion test. So next we are going to look at chi-square contingency table. So I have parked ANOVA at the end because ANOVA is slightly lengthy, right? So that's why I thought we'll solve all the other hypothesis testing exercises before looking at the ANOVA exercise. Now let us look at chi-square contingency table. As I told you, chi-square contingency table is also referred as test for dependency. So when we perform this exercise, we will be trying to validate whether the y variable is dependent on the x variable. So y variable will be your effect variable. X variable will be your cause variable. So through this exercise, we are trying to validate whether the effect variable is dependent on the cause variable or not, right? Because the dependent variable or the y variable, the effect variable, right? So will be dependent on some cause. So whether the y variable is dependent on this particular cause or not is something we will try to validate through this chi-square contingency table exercise, right? So let us frame the hypothesis statement straight away. And one more thing that I told you was the hypothesis statement will be in the form of a text. All the other hypothesis tests you would have seen, we would have incorporated the population notation of that relevant statistical metric and would have framed the hypothesis statements. But then in case of chi-square contingency table, the hypothesis statements would be in the form of a text. So what is the scenario? First, let us look at the scenario before even framing the hypothesis statements. So the below data pertains to the number of units sold for mobile brands A and B in cities 1 and 2. So obviously the sale of mobile brands will be considered as the Y variable, and we have two categories for this Y variable, mobile brand A and mobile brand B. And we are trying to validate whether the cities would actually trigger the sale of a mobile brand or not. So we have the data pertaining to two cities. So cities will be your X variable. And again, we have two categories for cities, city 1 and city 2. So having identified that sale of mobile brand is the Y variable and city is your X variable. So we need to validate whether the sale of mobile brand is dependent on the cities or not, right? So we have been provided with the input values pertaining to the number of units sold, right, for a mobile brand in both these cities, right? So number of units sold obviously will be a discrete value. So as I told you in chi-square contingency table, the input values will be provided as discrete values. So you will not find a continuous data provided as a input value in a chi-square contingency table exercise. Now we can frame the hypothesis statements for this. So H naught colon. So what will be a null hypothesis? When the dependency is yet to be proved, I will say that the y variable is independent of the x variable. So the sale of mobile brands is independent of the cities, right? And what is that we are supposed to prove through this exercise? HA colon the sale of mobile brands is dependent on cities. So this is what we need to prove through this chi-square contingency table exercise. Now let me just copy paste the entire table in the mini-tab worksheet and then perform the analysis. Right? And then we need to go to stat, and for a change, we are not going to click on basic statistics, we are going to click on tables, right? So this is chi-square contingency table. So stat tables, under that we have chi-square test. Click on that, and then we need to input the columns where we have the sale data, right? So the sale data is given in column mobile brand A and mobile brand B. So input all these, these two columns, which contains the sale values for mobile brand A and mobile brand B, and then we click OK straight away. So you get to see the p-value here, it is 0.033. So p-value less than 0.05, we need to reject the null hypothesis and accept the alternate hypothesis and conclude that the sale of mobile brands is indeed dependent on the cities. So as per the mini tab output, the p-value is 0.033. That is what we got, right? Yes. And what will be a statistical inference based on this? The statistical inference will be, since the p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis. And what will be a business inference? So the business inference will be the sale of mobile brands is dependent on the cities, right? So if you closely observe the input values here pertaining to the number of units sold, right, with regard to mobile brand A and mobile brand B, so we can find city 2 has the sale units more or less in the same proportion, right? City 2 has got the sale units more or less in the same proportion. But then if you look at city 1, we find mobile brand B being preferred by people in that city than mobile brand A, right? So that is why, probably we are getting a scenario where we are forced to reject the null hypothesis and accept the alternate hypothesis. The city number 1 seems to be preferring mobile brand B much more than mobile brand A. And this is the reason as to why we are getting a scenario wherein we are forced to reject the null and accept the alternate hypothesis. But then, looking at the input values, we cannot say that this difference is significant or not. Only after performing the analysis, we can come up to this conclusion, right? But then if you are using our template, we simply need to copy paste the input values alone. That's it, right? So you'll get to see the answers populating here. So this template can accommodate up to 5 columns and 3 rows, sufficiently big. And just copy paste the input values. You get to see the answers populating here. And finally, we also get to see the p-value along with the final inference. So reject the null hypothesis is the final inference. Right? So chi-square test stat value. So when we perform all these calculations using the manual formula, So we will first calculate what is called the expected values for each and every observed value. So the input value that is given here is the observed value. For each and every observed value, we'll arrive at the expected value using a formula. And with the help of observed and expected value, we will arrive at the chi-square value for each and every cell. And finally, we will come up with the total chi-square value. Based on that, we will arrive at the p-value. Based on that, we will come up with the final inference, right? But then if you're using the template, all these calculations will be done at the back end and you'll get to see the answers. So chi-square, the total test stat value is 4.565. That is what our template is also displaying. Fine. So this is about chi-square contingency table. So now let us look at ANOVA, analysis of variance. So even though it is called as analysis of variance, it is actually a mean test. So when we have or when we want to compare the population means of more than two population categories, then we need to perform this exercise called ANOVA, right? So look at exercise number 1, which says that please find below the sample time taken to produce a unit provided for 3 production centers. Test whether the mean time to produce a unit pertaining to these 3 production centers are equal or not. So as I told you, if you want to compare the population means of more than 2 population categories, then we need to perform this ANOVA exercise. So if there had been couple of population categories for which we wanted to compare the population means, then we would have performed the 2 sample t-test. But then when we have 3 population category means to be compared, so we need to use ANOVA for this case scenario. So what are the 3 population categories here? Production center A, production center B, and production center C. And what is that we need to compare? So we need to compare the mean time, the population mean time to taken to produce a unit item pertaining to all these 3 production centers. So we have been provided with the sample data, right, pertaining to the time taken to produce a unit item. So with this sample data that has been provided for all the 3 production centers, we need to validate whether the population mean of the time taken to produce a unit item pertaining to all these 3 production centers are equal or not, right? Then, so we need to perform this exercise called ANOVA, but even before we proceed with this ANOVA exercise, we need to ensure that couple of conditions are fulfilled before we proceed with this ANOVA exercise. So conditions for performing ANOVA. Conditions for performing ANOVA. The first condition is, which is an obvious condition, because unless and until the data distribution is normal, we cannot even apply mean as a statistical metric. So ANOVA is a hypothesis test for mean, right? So we can't even apply mean as a statistical metric. So first and foremost, we need to validate the normality of the data set, right? So first condition will be the response variable or the response data distribution should be normal, right? That is the first condition. Then only we can even apply this metric called mean. So the response data here is nothing but the time taken to produce a unit. So the response data distribution should be normal. So we need to perform the normality test for this data set. All the data points put together. So it will form a data set. And for this data set, we will perform a normality test as we did earlier. And what is the second condition? The second condition says the variances in the response data for the multiple categories of a factor should be equal. So this is yet another condition for performing ANOVA. So what it says, the variances of these three production centers should be equal. So we need to perform the variance test, right? So what is that variance test that we will use here? So when we want to compare the population variances of more than two population categories, then we need to perform the Bartlett's test. So Bartlett's test is what we are supposed to perform in order to validate the second condition. It says that the variances in the response data. So the variances in the time taken to produce a unit for the multiple categories. So the multiple categories are production center A, production center B, and production center C in this case scenario. Of a factor, what is the factor? Production center is the factor, should be equal. That means the variances of these three production centers should be equal. So that is the second condition, right? So let us see whether this particular scenario fulfills both these conditions or not. So for that, what I'm going to do, I'm going to arrange all these data points in a vertical structure. So let me just copy paste using the transpose function. All these data points should be arranged in a vertical structure. Right? And just by the side, I will also provide the production center reference. So the first four data points belong to production center A, and the next four production center B, and the final four production center C, right? So let me just copy paste all these input values in the Minitab worksheet and then perform the normality test. So the first column is the production center reference, and the second column is the time taken to produce a unit item. So first let us perform the normality test. So stat basic statistics and then the normality test. And what is the variable here? Time is the variable. So double click on this column containing the time data, and we are anyway going to perform the Anderson-Darling test. So we can straight away click OK. So we get to see the p-value. So p-value is what we need to see for making an inference as to whether the data distribution is normal or not. So p-value is showing as 0.085. So p-value is greater than 0.05. Then what is that we need to conclude? We need to conclude that the data distribution is normal. So in case of normality test, so what will be the null and alternate hypothesis? So let me just give the title as normality test. And what will be the null and alternate hypothesis statements? The time data distribution is normal will be my null hypothesis. So normal is the ideal scenario. So as I told you, if you look at a group of people, you'll always, think the status quo thought process about that group will be people are normal. So abnormality will be an exception. So which will be part of my alternate hypothesis because that is what we would need to prove, right? If someone is abnormal, we need to prove that. Right? Otherwise, I will continue to think that people are normal. So similarly, in a data distribution, my ideal assumption or the status quo assumption will be the data distribution is always normal. So abnormality or non-normality will be an exception. So alternate hypothesis will be the time data distribution is non-normal. Right? Now let me paste the probability plot and then provide the inference for this. So what will be the inference? The inference will be since the p-value is greater than 0.05 for 95% confidence level, we will accept the null hypothesis and conclude. I'm just combining the business inference as well, the same sentence, and conclude that the time data distribution is normal. So since p-value is greater than 0.05 for 95% confidence level, we will accept the null hypothesis and conclude that the time data distribution is normal, right? So the first condition is fulfilled. Now moving on to the second condition. So as I told you, for the second condition, we need to perform the Bartlett's test. So this is for equality of variances. So Bartlett's test is for equality of variances. Suppose you want to compare only two population variances, then we would perform two sample variance tests, as we did for one of the earlier case scenarios, right? So which will be the F test. But here we have three categories given, and we have been asked to validate whether the variances of these three categories are equal or not. So we need to perform the Bartlett's test. So for the Bartlett's test, what will be the null and alternate hypothesis statements? So the null hypothesis, so we are talking about variance. So what is the population notation for variance? You should not forget sigma square. So sigma square of production center A is equal to sigma square of production center B is equal to sigma square of production center C. So this will be my null hypothesis, right? So I'm going to assume that the variances of all these three production centers are equal. So that will be my null hypothesis. Alternate hypothesis will be, so I can either write the alternate hypothesis statement as sigma square A is not equal to sigma square B, sigma square A is not equal to sigma square C, sigma square B is not equal to sigma square C, and so on. But then instead of writing in detail, I can simply sum it up saying at least one pair is different. So even if sigma square A is not equal to sigma square C, then we will be rejecting the null and accepting the alternate hypothesis. So alternate hypothesis can be summed up as at least one pair is different. At least one pair is different. Now, having framed the hypothesis statements, now let us calculate the p-value using Minitab. So go to Minitab and then click on Stat and ANOVA. Under ANOVA, we have test for equal variances. So Stat, ANOVA, and under ANOVA, we have test for equal variances. What is the response variable? Time is the response variable. What is the factor? Production center is the factor. And we straight away click OK. And look at the p-value for the Bartlett's test. So p-value for the Bartlett's test is 0.958. So as per the Minitab output, the p-value is 0.958. So what will be your inference? The inference will be, since the p-value is greater than 0.05 for 95% confidence level, we will accept the null hypothesis and conclude that the population variances in time pertaining to all the three production sectors are equal. So the equality of variances has also been established, right? So both the conditions are fulfilled. Now we can perform ANOVA. But then we will get a scenario wherein the first condition may not be fulfilled. In that case, we don't even need to go and see if you are fulfilling the second condition. So the first condition, that is the data distribution is not normal, right? It has failed in the normality test. Then what is that we are supposed to do? If the data distribution is not normal, then we need to apply median as the statistical metric instead of mean, right? And in that case, we will use the equivalent median test for ANOVA, which is Kruskal-Wallis test. So let me just provide that information here. So if the first condition is not fulfilled, thus the response data distribution is not normal. So we cannot use mean as the statistical metric, and we need to apply median as the statistical metric, right? So hence we need to perform the equivalent median test for ANOVA, that is Kruskal-Wallis test. So I had mentioned couple of tests as equivalent tests for ANOVA, couple of median tests as equivalent tests for ANOVA. One is the Kruskal-Wallis test and the other one is the Moots median test, right? But then we need to know when to apply Kruskal-Wallis test and when to use Moots median test. So if the data distribution itself is proving to be non-normal, then we need to apply Kruskal-Wallis test, which is a median test. But then you can also get a scenario like this, wherein the first condition is fulfilled, but the second condition is not fulfilled, right? So if the first condition is fulfilled and the second condition is not fulfilled, so how this will look like? So the data, the response data distribution can be normal as well as random. So p-values will be greater than 0.05 for both these scenarios, normal and normality test and randomness test, right? But the variances of the multiple categories of a factor are not equal. So wherein we will have a p-value less than 0.05, right? So we will have a p-value less than 0.05 for the Bartlett's test. So in that case, we can understand that the variances are not equal, right? So if the variances are not equal, then what is that we need to do? So here again, we cannot perform ANOVA. We need to perform the equivalent median test called Moots median test. So we cannot perform ANOVA and we need to perform the equivalent median test, thus Moots median test, right? So now this is very clear as to when we are supposed to apply Kruskal-Wallis test and when we are supposed to use the Moots median test, right? So there can be a question on this. So they would have given a scenario, something similar to what I have written. So the response data distribution would be normal and random. So they would have given the p-values for both these scenarios as greater than 0.05. But then they would have mentioned that the variances are not equal. So they would have shown the p-value as less than 0.05 for the Bartlett's test. Then they will ask, which hypothesis test needs to be applied for this scenario. So we need to pick the option Moots median test. So data distribution is normal and random, but then the variances are not equal. We still cannot perform ANOVA. We need to perform median test called Moots median test. So we need to pick the option Moots median test as the right one for that case scenario, right? So similar question can come in the black belt final assessment. So that is why I made this in bold font. But as far as this exercise is concerned, there is no issue at all. We can proceed with the ANOVA exercise, right? So since both the conditions are fulfilled, we can proceed with the ANOVA exercise. Right? So what will be the null and alternate hypothesis statements for ANOVA? Anyone? So what will be H naught colon? So what is the population notation that I'm supposed to use? Quickly. So we need to use the population notation called mu, right? So mu is the population notation for mean. So this is a mean test. So mu of production center A is equal to mu of production center B is equal to mu of production center C. So this will be my null hypothesis statement. So when we are not yet proved that the population means are different for these three production centers, I will assume that the population means are equal for all these three production centers, and that will be my null hypothesis. And the alternate hypothesis, again, I'm going to sum it up saying at least one pair is different. Because I need not keep writing mu A is not equal to mu B, mu A is not equal to mu C, mu B is not equal to mu C, and so on. So I will just sum it up saying at least one pair is different. That's it. So this will be my hypothesis statements for this ANOVA exercise. Now, when we perform this ANOVA exercise, we would be filling in this table called ANOVA table. So all the output values will be filled in this particular table called ANOVA table. So we need to understand what are all the contents that will be part of this ANOVA table. So if we can understand the column headers that are given here, so you would know what are all the contents we are supposed to provide under these column headers in ANOVA table. So based on this, we will be taking a final call as to whether we are supposed to accept the null hypothesis or reject the null hypothesis. So let us look at the column headers given in this ANOVA table. So the first column header is source. So when I say source, it is nothing but source of variation. So when I say source, it is nothing but source of variation. So there are two sources of variation given in this ANOVA table. So the first one is the production center. So production center, we all know, is the factor, right? So we have three categories under this factor called production center A, production center B, and production center C. But production center as such will be called as the factor, right? So when I say the variation contributed by the production center, it is nothing but the differences between the mean values pertaining to all the three production centers. So that is the variation contributed by the production center as a factor. So again, I repeat. So if you are going to calculate the variation contributed by the production center, it is nothing but the differences between the mean values pertaining to all the three production centers, production center A, production center B, production center C. So basically through this ANOVA exercise, we are only trying to find out whether the differences between the mean values of all these three production centers is significantly different or not, or is significant or not. So that is the main intention of performing this ANOVA exercise, right? So production center variation or the variation contributed by the production center is nothing but the differences in the or differences between the mean values pertaining to all the three production centers, right? And this is what we are trying to validate through this ANOVA exercise, whether the differences between the mean values of all the three production centers is significant or not, right? So that is what we are trying to validate. Now, if the differences between the mean values is not all that high, then in that case, we will say that the population mean values of these three production centers are more or less the same. Then we will not have sufficient evidence to reject the null hypothesis, right, in this ANOVA exercise. But then if you are going to observe that the differences between the mean values for all the three production centers is significant, then in that case, we need to infer that the differences is significant and we'll be rejecting the null hypothesis and accepting the alternate hypothesis, which says at least one pair is different. So the mean of production center A could be significantly different from B, or mean of production center A could be significantly different from C, or mean of production center B could be significantly different from C. So even if one of the pair is different, then in that case, we'll be rejecting the null and accepting the alternate hypothesis, right? But how to find that the differences between the mean is quite significant? The differences between the mean of three production centers is quite significant. So we would want to compare this with some base variation. Then only we can say that the variation contributed by the production center, that is the differences between the mean values pertaining to all the three production centers, is significantly high, right? So we would want to compare this with some base variation. Unless and until we compare it with some base variation, we cannot say that the differences between the mean values is significant. So when can we say that the differences between mean values is significant? So it has to, exceed a criteria. What is the criteria? And that is the base variation that we are considering here. And that base variation is what we would call as the error variation. So the error variation is nothing but the common cause variation. And what is the common cause variation here? So the common cause variation is nothing but the variation that you would find within these data points pertaining to a production center. Same production center, same type of units, but the time taken is going to differ slightly. Then the difference could be attributed to common cause variation, right? And that is the minimum variation that we can observe in any process, in any system. And that is what is referred as error in this ANOVA table. Clear? So error variation will be considered as the base variation. So if the differences between the mean is not even greater than that error variation, then in that case, we do not have sufficient evidence to reject the null hypothesis. And we will conclude that the mean values of all the three production centers are more or less the same. But then if you find the variation contributed by the production center as indicated by the differences between the mean values of all these three production centers is significantly higher than the error variation, then we can safely conclude that at least one pair of mean values is significantly different, right? So that is exactly what we are going to do as part of this ANOVA exercise. Fine. So what is this error variation, which is also denoted as common cause variation? So this is nothing but the variation within the data points pertaining to a production center. So the data points pertaining to a production center. So the variation within the data points is what we would call as the error variation or the common cause variation. So the production center variation will be compared with the error variation in this ANOVA exercise. And if the production center variation is going to be significantly high, then we are going to conclude that the differences between the mean values pertaining to all these three production centers is quite significant. On the other hand, if the production center variation is more or less same as the error variation, then we are going to conclude that the differences between the mean values of all these three production centers is not significant, right? So the next column, we have SS. Now I need to calculate the variation contributed by the production center and also the variation contributed by error, which is the common cause variation. So the first step, we need to find out sum of squares, which is denoted by SS. So the full expansion is sum of squares. And this sum of squares is nothing but the numerator in the variance formula. So if you remember, what is the numerator in the variance formula? So let me just go back to the notes file and we'll click on the measure sheet. And if you scroll up to the top, we will find the formulas written here. So I've written the variance formula. So what is the variance formula? Summation of square deviation of each and every data point in the data set from the mean value. And this numerator is what we would call as sum of squares. So sum of squares is nothing but the numerator in the variance formula. Clear? And what is DF, which is the next column header? So this is degrees of freedom. DF is nothing but degrees of freedom, and this can be calculated by applying the formula sample size minus 1, n minus 1, right? So sample size minus 1 is the denominator in the variance formula. So if you see, sample size small n minus 1 is the denominator in the variance formula, right? So we are actually calculating this variance metric for both production center as well as for error. So this is the denominator in the variance formula. Now, the third column or the fourth column here in the ANOVA table shows sum of squares, degrees of freedom, and then we find MSS. MSS, the full form is mean sum of squares. And mean sum of squares is actually the variance, right? This is actually the variance calculation. And what is this mean sum of squares? So this is MSS is sum of squares divided by the degrees of freedom. So the sum of squares will be the numerator in the variance formula. Degrees of freedom will be the denominator in the variance formula. So sum of squares divided by degrees of freedom is nothing but the variance calculation, right? So mean sum of squares of production center will be the variance of production center. Mean sum of squares of error will be the variance of error, right? Now I need to compare the variance of production center with the variance of error. So if the variance of production center is significantly higher than the variance of error, then we can conclude that at least one pair of mean values is significantly different, right? We'll be rejecting the null and accepting the alternate hypothesis. So that we will know when we calculate this F-calc value. So F-cal is nothing but F calculated value, right? So this will be mean sum of squares of the factor, which is the production center, and mean sum of squares of error, because we need to compare these two variations, right? So the variation contributed by the production center divided by the variation contributed by the error. So the variation contributed by the production center is going to be significantly high compared to the variation contributed by the error. What will be the resultant F calculated value? That will also be a higher value. Is it not? So the numerator is going to be significantly higher than the denominator, then the resultant value also will be a very high value. It's a mathematical logic. So how far it should be high or how much it should be high? It should be higher than the table value. So F tab is what we would call as the F table value, right? So this can be obtained by using the Excel formula. So if you find F calculated value greater than the F table value, then we can infer that at least one pair of mean values is significantly different, right? But then on the other hand, if F calc value is less than the F table value, that is, it is not even greater than the table value, then we can infer that the population means of the multiple categories of a factor are equal. That means we'll be accepting the null hypothesis, right? F calculated values less than the table value, we can infer that the population means of the three production centers are more or less the same, are equal. So we don't have sufficient evidence to reject the null hypothesis. We'll end up accepting the null hypothesis. So this can be reconfirmed by calculating the p-value at the end. So by looking at the F calculated value or comparing the F calculated value with the table value, we can come up with the final decision as to whether we are supposed to reject the null hypothesis or accept the null hypothesis. So F calc value greater than table value, we will reject the null and accept the alternate hypothesis. F calc value less than the table value, we will continue to accept the null, which says that the mean values are equal for the three production centers. Clear? And we can reconfirm this decision by calculating the p-value. So this is what we are going to do now. So let me just quickly calculate all these things manually, but then you don't have to perform any manual calculation because I have given the template for ANOVA as well, right? Wherein we just need to copy paste the values. The ANOVA table will get populated automatically. So you'll find this in a short while. So before that, let me just perform the calculations. So for calculating the sum of squares, I will first and foremost obtain a value called grand total the whole square divided by the sample size. So the grand total whole square will be sum of all these data points. Sum of all these data points, the whole square, divided by how many data points are there? So 4 per production center. So 4 into 3. So we have total of 12 data points. So let me just park this value aside. We will use it for calculation of sum of squares. Now, sum of squares calculation for the production center. So I need to sum the data points pertaining to each and every production center and then square it divided by how many values I have considered? 4 values divided by 4 plus sum of squares of production center B, the whole square divided by 4 plus the square of or the sum of squares of the data points pertaining to production center C divided by 4. So the whole thing should be subtracted from the grand total square by n value, which we have already calculated. This value. That's it. Right? You'll get the sum of squares for production center. Now, instead of straight away calculating the sum of squares for error, we will first calculate the total sum of squares. And from that, I will calculate the sum of squares of error. So the total sum of squares, what we need to do, we need to square each and every data point here and then sum it up. Plus 5.1 square plus 5.2 square plus 5.3 square. Second row, 5 square plus 5.2 square plus 5.1 square plus 5.2 square plus the final row, 4.7 square plus 4.8 square plus 4.7 square plus 4.9 square. So the entire thing should be subtracted from the grand total square by n value, which is in cell O104 or O105. That's it, right? So you can just round this off. And now I can calculate the error sum of squares. So how I will calculate the error sum of squares? So production center sum of square plus error sum of square will be total sum of square. Or total sum of square minus production center sum of square will be error sum of square. So total sum of square minus the production center sum of square will give you the error sum of squares. Now for calculating the degrees of freedom. So how many categories are there for production center? So in this case scenario, we have 3 categories for production centers. So degrees of freedom will be n minus 1. So 3 minus 1. Now instead of calculating error degrees of freedom, I will calculate the total degrees of freedom. So how many data points are there in total? We have 12 data points in total. So total degrees of freedom will be 11. So what will be the error degrees of freedom? It will be total degrees of freedom minus the production center degrees of freedom. So 9 is the error degrees of freedom. And mean sum of squares for production center will be sum of squares divided by the degrees of freedom. Similarly, mean sum of squares of error, sum of squares divided by error degrees of freedom. Now, I need to compare these two and then arrive at the F calculated value. I can simply divide the mean sum of squares of the production center divided by the mean sum of squares of error. So get a value 24.7. So that is the formula for calculating the F calc value, mean sum of squares of factor divided by mean sum of squares of error. So we get a significantly higher value is 24.7. So it will be definitely greater than the table value. So even if you are going to calculate the table value, you'll be able to find that out. So what is the table value calculations? I told you we need to apply the Excel formula. For table value, it will be F dot INB. 95% is the confidence level, so probability will be 0.95. And the degrees of freedom for production center is 2, and for error it is 9, and close the bracket. So table value is only 4.26, whereas the F calculated value is 24.7, significantly high, indicating that the variation contributed by the production center is significantly higher than the error variation, meaning the differences between the mean values of the 3 production centers is quite significant, right? So we can reconfirm our decision by calculating the p-value. So p-value can be calculated by applying the Excel formula, is 1 minus f dot dist. You need to provide the calculated value as the reference, comma, degrees of freedom will be 2, 9, and cumulative will be 2. That's it. So p-value is showing as 0. So 0 means less than 0.05 for 95% confidence level. So we need to reject the null hypothesis and accept the alternate hypothesis, which says at least one pair is different. So let us provide the statistical and the business inference. So you look at the p-value, right? Or you can even write, since the f-cal value is greater than f-table value, or the p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis. So what will be business inference? The business inference will be the population mean time taken to produce a unit item is significantly different for at least one pair of production sectors. So is at least one pair of production centers. So the population mean time taken to produce a unit item is significantly different for at least one pair of production center, right? So if you are going to calculate the sample mean, we'll get some idea as to which production center seems to be having a different mean value, right? So let us calculate the sample mean and then try to find out. So sample mean, I'll just consider the sample data points to calculate the average, right? So 5.2 is the sample mean for production center A. Now if you see production center A and B, the sample mean values are more or less the same. But then if you look at production center C, the sample mean value seems to be significantly lesser compared to the other two production sectors. So, if at all there is a significant difference in the mean values, it is because of production center C, which seems to be having a significantly lesser mean value compared to the other two production centers. So, production center C has a significantly lesser mean value compared to the other two production sectors, right? So if you are going to solve this using Minitab, we already have the data entered in the Minitab worksheet. So we can straight away perform the calculations. So stat, click on ANOVA. It is called as one-way ANOVA because we are considering only one factor here. Production center is the single factor that we are considering in this exercise. So this factor may have three categories, but the factor is only one factor, that is production center. So this will be one-way ANOVA, right? So the response is time and the factor is production center. And we can straight away click OK. So as we can see, the confidence interval that we have built for the sample mean values for all the three production centers, we find the confidence interval to be overlapping for production center A and production center B, which means the population means of these two production centers are more or less equal, right? But if you look at production center C, the confidence interval that we have derived is not overlapping with the other two production centers. So it is looking distinctly different. So that is why the population mean value for production center C will be far lesser than the other two production sectors. So they are different. Now, if you look at the ANOVA table, you can validate all these values that we calculated. So production center sum of squares is 0.41167. 0.41167. Error sum of squares 0.07500. And total sum of squares 0.48667. 0.48667. Straight away going to F calculated value 24.7, P value is 0. 24.7, P value is 0. Perfect. Right? But then if you are going to perform this calculation using our template, it's going to be very, very simple. We simply need to copy paste the input values. That's it. So this template can accommodate up to 5 columns and 4 rows. You can simply copy paste the input values. You can see the ANOVA table populating automatically. So F calculated value 24.7, table value 4.26, p value 0. Inference will be reject the null hypothesis and hence accept the alternate hypothesis. Clear? So this is how we'll perform this ANOVA exercise. So we'll have a 15-minute break. So when we come back, we'll look at the exercises under correlation and regression analysis. But before that, let me just make an announcement. So tomorrow it's going to be the final day of this training session, right? So on the final day of this training session, let us take a group photograph through Zoom. So I would appreciate if you all could come on video, at least for a minute, right? Just for a minute, if you all could come on a video, so we can, take the group photograph through Zoom, and this group photograph will be published in LinkedIn. So this group photograph will be published in LinkedIn. Anyway, I'll send you a message tomorrow morning. Then I just wanted to give you a heads up. So if at all right, if you want, you can just, come on video at least for a minute. So I would appreciate if you all could come on video to look nice, right? So for a group photograph, instead of having only the names, right, on the screen. So if you can just show your faces, then it look nice. All those smiling faces, you can take a group photograph and then publish it in LinkedIn. Just a request from my side, right? So just be prepared and just giving you a heads up. So anyway, tomorrow morning, I'll just send you a WhatsApp message. Fine. So now we will have a 15-minute break. Thank you. Thanks a lot. Hello friends, I am back. Hope you're all back as well. So let us continue with the correlation and regression exercise. So I'll click on the next sheet, title correlation and regression. Right. So we have a case scenario wherein the two variables that are provided are experience levels of the associates in months and the average processing time. So we have been asked to validate whether these two variables are correlated, and if so, we need to build the regression model in the format y is equal to f of x plus epsilon. So out of these two variables, which one is the x variable, which one is the y variable? So we have experience levels of the associates and average processing time as the two variables in this exercise. So out of these two variables, which one is the x variable, which one is the y variable? Obviously, the experience levels of the associates will be my x variable, and the average processing time, which is the ultimate impact that would be experienced, will be my y variable, right? And for this particular scenario, if you would remember, we have already constructed the scatter plot, right? So we already constructed the scatter plot for this scenario, and we could observe a downward slope-like formation of data points when we plot the values for the x and y variables, right? So when we plot the data points pertaining to the experience levels and the average processing time, we could get a downward slope-like formation of data points in the scatter plot, indicating that these two variables are negatively correlated. So if you happen to observe a downward slope-like formation of data points in a scatter plot, then we need to infer that the two variables are negatively correlated. So we know that experience levels of the associates and the average processing time are negatively correlated post performing that scatter plot exercise. But what is the strength of this negative relationship is something we would be able to ascertain only when we perform the correlation analysis, right? So only when we calculate the correlation coefficient value, we will be able to clearly tell the strength of that negative correlation, right? So let us perform that. Let us calculate the correlation coefficient value, which is small r. So correlation coefficient denoted by small r can be calculated by applying the Excel formula is equal to CORREL. CORREL, and we need to provide the range of the X data set, comma, without leaving any gap, provide the range of the Y data set, and then close the bracket and click on enter. So you'll get to see the correlation coefficient value. Just round this up to 3 decimal places. We get minus 0.925. So the negative sign uh, in this correlation coefficient value clearly indicates that these two variables are negatively correlated. So when it is minus 0.925, then what can you tell about the strength of the relationship? So if you go to the analyze sheet and refer to this table, right, wherein I have provided the inference that we need to come up with for a given correlation coefficient value. So if the correlation coefficient value is going to be less than minus 0.85, then we need to infer that there is a strong negative correlation between the two variables, right? So we have the correlation coefficient value as minus 0.925, and hence we need to infer that there is a strong negative correlation existing between the two variables. So let me provide the inference for this. So since the correlation coefficient small r value is less than minus 0.85, we can infer that the experience levels of the associates and the average processing time have strong negative correlation between them, right? So this is the inference that we can come up with. So now we can perform the regression analysis. So the next step would be to perform the regression analysis, right? So as part of regression analysis, before we even build that regression model in the format y is equal to f of x plus epsilon, we first need to establish that the experience levels of the associates is a significant factor influencing the average processing time. Just because these two variables are correlating with each other, we cannot say that one is the cause for the other. So correlation and causation are two entirely different terminologies, right? We need to understand the difference between correlation and causation, right? So say for example, so kids, consuming lots of tomato juice will be high on obesity, right? So there could be a scenario wherein kids consuming lot of tomato juice could be high on obesity. So if you are going to, calculate the correlation coefficient, then it could turn out to be a positive correlation between these two variables, right? So consumption of tomato juice and high obesity may be positively correlated. Just because these two variables are positively correlated, can I say that consumption of tomato juice is the reason or the cause for high obesity in the kids? Definitely not, right? So we need to establish that separately. So here again, just because the experience levels of the associates and the average processing time are negatively correlated, we cannot say that the experience levels of the associates is the cause for the average processing time. So we need to establish that the experience levels of the associates is a cause for the average processing time before building the regression model, right? So here what I'm going to do, I'm first going to establish that the experience levels of the associates is a regressor for the average processing time. So just because experience levels and average processing time are negatively correlated, we cannot say that experience levels is the cause for the average processing time. So correlation and causation are different. Hence, we first need to establish that the experience levels of the associates is a regressor. So when we say that this factor has a significant influence on the y variable, so we will call that as a regressor. So experience levels of the associates is a regressor for the average processing time. So this has to be established first, right? And then we can construct the regression model, right? So for establishing that the experience levels of the associates is a regressor for the average processing time, so I need to frame the hypothesis statements. So the null hypothesis for this scenario will be experience levels of the associates is not a regressor, because I want to prove that the experience levels of the associates is a regressor. So that will be my alternate hypothesis. So before proving that experience levels of the associates is a regressor for the average processing time, I will assume the status quo scenario as experience levels of the associates is not a regressor for the average processing time. And the alternate hypothesis which we need to prove, experience levels of the associates is a regressor for the average processing time, which we need to establish, right? So we'll perform this exercise using Minitab. So let me just erase all the input values pertaining to the previous exercises, right? So let me just copy paste this. Right. So where I need to go to stat, and then I find regression, and once again regression. So the response variable is average processing time, predictor is experience levels of the associates, and we click OK, right? So here itself, you can find the ANOVA table, and you find the p-value for the experience levels of the associates as 0.000, right? So that is the regression, right? It's not given as experience levels of the associates, but that is the regressor here. So regressor, the p-value is 0.000. So p-value is less than 0.05, we'll be rejecting the null and accepting the alternate hypothesis. So I write as per the Minitab output, the p-value is 0.000. So what will be your inference? The inference will be, since the p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis. So we can conclude that the experience levels of the associates is a regressor for the average processing time. Now, having established that experience levels is a regressor for average processing time, now we can proceed with the model building exercise. So now let us proceed with the regression model building exercise. So we can build the regression model using an Excel formula, or you can even refer to the Minitab output, right? So first we will calculate the values using the Excel formula. So what are the values that we need to get? So the first one is the coefficient of the X variable. So here the X variable is the experience levels of the associates. So that will have some coefficient value, and that coefficient value will be a negative value. So why it will be a negative value? Because the experience levels of the associates and the average processing time are negatively correlated. So this coefficient of experience levels of the associates, which is nothing but your X factor, will also be a negative value. And then we will also calculate the constant value. This constant value would represent epsilon in the regression model. And that epsilon would denote the common cause variation, right? We all know that. So constant value can never be equal to 0 in a practical scenario. So it will always contain some positive value. So variation matrices cannot take negative values. It will always contain positive values. So common cause variation metric also will contain only the positive value. So since I need to calculate two values through a single formula, so first and foremost, I need to highlight these two cells and then apply the Excel formula is equal to linear estimate. In short, it is linest, L-I-N-E-S-T, right? And then open bracket. So first we need to provide the range of the Y data set, known Ys, right? And then comma, without leaving any gap, we need to provide the range of the X data set, known X's, comma, I want this to be calculated normally, so provide this parameter as true. And I do not want any additional regression statistics, so provide this parameter as false. Close the bracket. Now we should not straight away press enter because we would require two values. One is the coefficient of x and the other one is the constant value, right? So since we would require a couple of values, we should not straight away press enter. So what we need to do is we need to press shift, control and enter simultaneously. Once we do that, we get a couple of values here. So the coefficient of the x variable, which is the experience levels of the associates, is a negative value because the experience levels of the associates and the average processing time are negatively correlated. Then we find the constant value, which is the epsilon value, right, greater than 0. So it is a positive value. So variation matrices cannot take negative value. We all know that. Now I can build the equation. So the regression model will be average processing time. Let me just kind of adjust the intent. So let me just provide the regression model. Average processing time is equal to, so since the constant value is a positive value, I'll just place that in front. So 26.3 minus 0.371 into experience levels of the associates. So this will be my regression model, right? So this is the format y is equal to f of x plus epsilon. But then if you want to validate whether the regression model is best fit or not, we need to calculate regression coefficient. So what is this regression coefficient? So this is denoted by capital R square, right? So regression coefficient will be square of this correlation coefficient value. We simply square this correlation coefficient value, we get the regression coefficient and round this up to 4 decimal places. So we get the value 0.8550 or 85.5%. So anything above 85%, we can infer that the model is best fit, right? So here again, I can infer since the regression coefficient R square value is greater than 0.85 or 85%, we can infer that the regression model is best fit. So when the regression model is best fit, we can substitute any value for the x variable and we can obtain the answer for the y variable. So let us do that. Suppose the experience levels of the associates is 14.25 months. So what will be the average processing time? So the experience level of the associate is 14.25 months. Then what will be the average processing time? Average processing time will be, just apply this value in this equation. So what is this? 26.3 minus 0.371 multiplied by, instead of experience levels of the associates, we need to substitute this value 14.25 multiplied by 14.25. That's it. So this will be 21.01 minutes. 21.01 minutes. Right? So this is how we can actually calculate once we find that the model is best fit by looking at the regression coefficient value, which is the R square value. So if it is greater than 0.85 or 85%, we can conclude that the regression model is best fit. So in that case, we can substitute any value for the x variable and get the answer for the y variable, right? So we can also use the template to perform all these calculations, including that ANOVA table, which actually helped us to establish that the experience levels is a regressor for the average processing time. So what we need to do, we simply need to copy paste the input values. That's it. Once we copy paste the input values, we can refer to the solution section. So the correlation coefficient value is minus 0.925 and the regression coefficient is 0.8550. So the coefficient of x is minus 0.371, rounding it up to 3 decimals. Constant value will be 26.3, again rounding it off to single decimal, and the model is best fit. So on our table, the F calculated value was 106.12 and the P value was 0, which would mean that the X factor is a regressor. That is, the experience levels of the associates is a regressor for the average processing time. So if you are going to look at the Minitab output, we already seen this ANOVA table. So F calculated value is 106.12. So that is what our template also displayed. And if you look at the R square value, it is 85.5%. And that is exactly what we also got, right? 85.5%. And then if you look at the regression model, is given at the top, right? Average processing time is equal to 26.3 minus 0.371 into experience levels of the associates. And that is exactly what we also got. Average processing time is equal to 26.3 minus 0.371 into experience levels of the associates. But then remember, I had told you while discussing about the importance of common cause variation and while demonstrating that common cause variation is inevitable in any process, in any system during the introduction phase, I had mentioned that the common cause variation can never be equal to 0 and we will not get all ideal values for the y variable given some value for the x variable, right? If you remember, so let us go to the introduction sheet, right? We looked at this particular scenario, advertisement cost and sales, right? And we assume the relationship to be sales is equal to 2 times the advertisement cost. So I told you at that time that for each and every instance of investment that you make towards the advertisement cost, we cannot get all ideal values for sales in a practical scenario, right? So even if this relationship holds good, the actual value for sales could be slightly differing from the ideal value. It will be closer to the ideal value, but we may not get ideal values for sales for each and every instance of investment towards the advertisement cost, right? So this we had clearly seen at that time. So this difference between the actual and the ideal value for the y variable is what we would attribute due to common cause variation. And we could understand that the common cause variation can never be equal to 0 in a practical situation, right? So let us actually cook up a data and then let us see, how the common cause variation will be 0 when we can, consider only the ideal values for the y variable given some values for the x variable. And then we will also see, what are all the various anomalies that we will be able to observe because the common cause variation is 0. So let me again consider advertisement cost and sales and then cook up the value. So I'm going to consider only the ideal value for the sales and then perform the regression analysis. So let me make the same assumption that sales is equal to 2 times the advertisement cost, which means if I'm going to invest $5 towards the advertisement cost, my sales will become 10. So $10 will become 20, 15 will become 30, 20 will become 40, 25 will become 50, 30 will become 60, 35 will become 70, 40 will become 80, 45 will become 90, and finally 50 will become 100. So let me consider 10 pairs of data. So I have considered only the ideal values for sales. As per that equation, sales is equal to 2 times the advertisement cost. That's it, right? So the actual value for sales has not been considered. So now if I'm going to perform regression analysis for this data set, so let me find out. So regression, and the response variable will be sales, and the predictor will be the advertisement cost, and we straight away click OK. So since the common cost variation will be 0 for this scenario wherein I have considered only the ideal values for the y variable. So we can see the error variation showing 0 here in the ANOVA table. And just now we actually understood that the error variation would represent common cost variation. So the common cost variation is showing as 0 here, right? And if the error variation is 0, then we will not be able to compare mean sum of squares of the x variable or the factor with the mean sum of squares of error, right? Because the error is showing as 0, and f calculated value cannot be calculated, and hence p value also cannot be calculated, and we will not be able to validate whether that x factor is a regressor for the y factor. Clear? So this is number one. Number two, we find the R square value to be exactly equal to 100%. And I told you this cannot be the case in a practical scenario. So if the R square is 100%, then common cost variation will be 0%. So that is what we get to see here. Common cost variation is 0. R square is showing us 100%, right? And if you look at the regression equation, so it shows the constant value as 0. Constant value would represent common cost variation in the regression model. So sales is equal to 0 plus 2 times the advertisement cost. So this kind of a scenario cannot exist in a practical situation, right? So we cannot have the constant value as 0 in the regression model, right? So that is another anomaly. So if I'm going to construct scatter plot, let us see how the scatter plot would actually look like. So I will choose the one with the regression slope, and the y variable is sales, and the x variable is advertisement cost, and we click OK, right? We find all the data points lying right on the slope. We cannot get a scenario like this in a practical situation, right? So we will not have all the data points pertaining to the y variable lying right on the slope, right? This is not possible at all. So looking at the scatter plot, we can clearly understand that, someone has dealt with the cooked up data, not the practical data. So we cannot get a scenario like this. Clear? So we will get a scatter plot, something like what we saw for this exercise, right? Experience levels and the average processing time. So we constructed the scatter plot, correct? So it will be appearing something like this. So maybe a couple of data points may fall right on the slope, right? Couple of data points may fall right on the slope. We are not ruling out that. But when we have 10 pairs of data points, it is quite unlikely that we will have all the 10 data points falling right on the slope. That is practically impossible. So we will have majority of the data points falling either above the slope or below the slope, right? It will be something like this. Maybe a couple of data points may fall right on the slope. We are not ruling out that, but majority of the data points would fall either above the slope or below the slope, not right on top of the regression slope. Now, if you want to understand what is the slope in this regression equation, so the slope is nothing but the coefficient value of the x variable. So there can be a question on this. So here, what is the coefficient value for the x variable? It is minus 0.371. So slope will be minus 0.371, right? So it will be the coefficient value of the x variable. Fine. So let us look at the final exercise for the day. So out of all the exercises that we solved today, this final exercise, the similar format can come as a question in the black belt final assessment tomorrow, right? So only this exercise number 2, a similar format can come as a question in black belt final assessment, right? So let us look at this exercise. It's a very simple one. So we have been provided with the regression model, that is profit is equal to $1,200 plus 100 into advertisement budget minus 325 into overtime hours. So there are two x variables in this regression equation. X1 is the advertisement budget, X2 is the overtime hours, right? And profit is the y variable, and 1200 is the constant value, which would represent the epsilon value in this regression model, right? So with this equation, we have been asked to estimate the profit if the advertisement budget is $500 and the overtime hours is 50, right? So what we need to do in this main equation, we need to substitute the values for the advertisement budget and the overtime hours and then calculate what will be the profit, right? So how can we do that? So if you want to manually perform the calculation or if you want to use Excel to perform the calculation, so we need to have profit in one column and we need to apply this formula. What is the formula? 1200 plus 100 into advertisement budget. So what is the value that I need to substitute for advertisement budget? It is given as 500. So put 500 minus 325 into overtime hours. So what is the value I need to substitute for overtime hours? It is 50. That's it. So you get the answer, $34,950, right? So what we can understand from this regression equation is that when we have a positive coefficient value for x variable, so we can infer that the x variable and the y variable are positively correlated. If you have a negative coefficient value for the x variable, we can infer that the corresponding x variable and the y variable are negatively correlated. So here we find advertisement budget having a positive coefficient value. So we can say that advertisement budget and profit are positively correlated. But then we have overtime hours, the coefficient value for overtime hours being negative. So we can infer that overtime hours and profit are negatively correlated. Just a piece of information that we can gather by looking at the regression equation. Or suppose you want to use this template to calculate the profit, we can do so. So what is the constant in that equation? 1200. And what is the coefficient of x1? That is advertisement budget plus 100. What is coefficient of x2? That is overtime hours. With the sign, it is minus 325. Right? We should not forget to put the sign. Value for x1, which we need to substitute in the main equation. So for advertisement budget, we need to substitute 500. Value for x2, which is the overtime hours, which we need to substitute, it is 50. So moment you provide all these input values correctly, you will get the correct answer, 34,090. Fine. Okay then, so let us stop here. So we will have the mock test conducted for the black belt assessment. So what I will do, I will send the procedure to access the test link once again. And I will also send the updated files to you through the common WhatsApp group. So tomorrow we will have the photograph taken just before our routine break, the 15-minute break. Okay. So as I did for the green belt mock test, I will send the correct answers for the black belt mock test sometime tomorrow morning. So you can just validate with yours. Now give me a couple of minutes so that I can send the updated files through the common WhatsApp group. I've sent both the updated files to the common WhatsApp group. You can download them and then start answering the mock test questions for the black belt assessment. So there will be a couple of questions pertaining to the design of experiments, which anyway we are going to see tomorrow, right? So for those questions alone, you can get the answers from me. For all the other mock test questions, I think you should be able to answer comfortably. But in case of any clarification or doubt, you can always check with me because I will be online for the next 30 minutes. But then I'll be on mute. So in case of any clarification required, so you can just unmute yourself and then ask me the question. Right? So all the very best to each one of you. So we can now start attempting the mock test questions for the black belt assessment.
Sir?
Yes, please.
Yeah. So after I entered the dashboard,
Yeah.
so the batch number says 278. Is that fine after the black belt? I
Yeah,
mean,
that's
after
okay.
I,
Now
yeah,
you clicked on the black belt
yeah,
certification program continue course, right? That
yes,
link.
exactly. Yeah,
Okay, so you will get to see all these training materials in the left-hand side
exactly.
pane,
Yeah,
correct? So just
yes,
scroll
yes.
down to the end.
Okay.
Just above the final test link, you will find the mock test link.
Yeah, right. Okay.
Yeah,
Yeah,
just click on that. Yeah, that's it.
sure. Okay. Okay. Thank you. Thank you so much.
Yeah. Once you complete the mock test, you can exit.
Hi, Sridhar.
Yes, please.
Uh, I have completed my mock test.
Okay. Yeah.
Uh, I have a doubt.
Yeah.
So tomorrow's exam will be like the same format, 20 questions within 30
No, no,
minutes.
no, no, no. Tomorrow's so format will be the same, but the number of questions will be 50, which you need to answer in 60 minutes.
Okay. Okay, 50 questions, 60 minutes.
So it will be multiple choice questions, but there will be 50 questions which you need to answer in 60 minutes.
Okay. 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 Can I drop
Okay?
now?
Yeah, yeah, please. We'll
Thanks.
connect
Thanks.
tomorrow.
Yes, yes,
Thank you.
please. Thanks.
Thank you.
Well, I'm done. I'm done.
Okay. Thank you.
Sure. Thank you.
Hi, Sridhar, I'm done. Thank you so much.
Thank you. Connect tomorrow. Thank you.
Sure.
Good night, sir. Thank you.
Good night. Thank you.
Thank you. Good night.
Good night. Thank you. So anyone still attempting the mock test?
Yes, sir.
Yeah.
Sir, I finished. Thank you. Good night, sir.
Thank you. Good night. We'll connect at the same time tomorrow evening. Thank you.
Okay, sir.